Dear students, welcome back. We have reached section 5.3.1 and section 5.3.2, and we will discuss the Martingale representation theorem first. Well, this theorem is used to justify that we can find a hedging portfolio XT. And remember, XT is equal to VT, the price of the option. So it's important to find a way to define the portfolio, which was composed of delta T ST plus a remaining part. And if we have a definition, if we have a formula for delta T, the number of stocks in the portfolio, that gives us a hint of how this portfolio for the writer looks like. So we will start by stating a theorem, the Martingale representation theorem, and we do it without a proof. The proof is a little technical, and it will be on the slides. It's not in the book. It's just in the slides for your information. It's measure theory based. So let me motivate the Martingale representation theorem. And first remember that we have seen before that an Ito integral is in fact a Martingale, and that looked like the integral from 0 to t gamma u dwu with respect to the filtration of the Brownian motion. And the Brownian motion is originally defined on some probability space, omega fp, and comes with its own filtration or with some filtration. And if we use this filtration to define the Ito integral. Now, the Martingale representation theorem tells us that the converse is also true. So we will look at the converse of this statement. It tells us that any Martingale can be expressed as an Ito integral. So it's really the converse. Here you see the theorem, the Martingale representation theorem. Let omega fp be a probability space and wt, little t between 0 and capital T, be a Brownian motion with a filtration script ft and little t again between 0 and t, which is generated by the Brownian motion. And here we need to be specific. And this script ft, it is the smallest filtration that you can consider as a filtration for the Brownian motion. To be more exact, the ft that I see here is the smallest sigma algebra that makes ws measurable for all s between 0 and little t. It contains things like ws is in some Borel set, and you take all such sets, and you look at the sigma algebra generated by it, but these are technical details that we will not discuss here. But you see, so it is a filtration, a specific filtration generated by the Brownian motion. It is this sigma algebra that I just mentioned. Now let MT be a Martingale, again, little t between 0 and capital T, with respect to that filtration FT. Then there exists an adapted process, gamma t, again, little t between 0 and capital T, with the requirements that the integrals exist. So remember the requirement. The requirement is that the expected value of the integral from 0 to t of gamma squared t dt is finite, exists. And so there exists an adapted process, gamma, such that mt is m0 plus the integral from 0 to t gamma u dwu. So m need not start at 0, and therefore we have mu0 included here. And remember that we always think of these adapted processes in such a way that they satisfy all the properties that we want for the Ito integral to exist. So this is just the converse. This says we have a Martingale, and then there exists a gamma. So there exists a gamma such that this Martingale is defined. Just the converse of the first statement that we have seen earlier. Now, as I mentioned, the proof is on the slides based on several claims, claim 1, claim 2, claim 3, but we will not discuss them. Yeah. Now, what we next bring you is a corollary 5.3.2, and that's a corollary that collects all the results that we have and that are important for us. And there's a little hidden technical difficulty, which will be resolved in exercise 5.5 in the book, and exercise 5.5 will be one of the exercises that is for you to discuss, for you to solve at some point. So the corollary starts as follows. Let Wt, little t between 0 and capital T, be a Brownian motion with a filtration, script Ft, again, little t between 0 and capital T, and it's generated by the Brownian motion. So remember again that Ft is then this sigma algebra of Ws with 0 less or equal to S less or equal to little t. Then let theta t be an adapted process, and then we define it as follows, of course. So we have the following properties. We define Zt is the e to the power minus the integral from 0 to t theta u dwu minus 1/2 the integral from 0 to t theta squared du. Again, assuming that all these integrals exist. And we have, moreover, we name z equal to z at capital T. Z is Ct. Then we have our Brownian motion, W tilde t, which is equal to Wt plus the integral from 0 to t theta u du. And we have seen all of these we have seen in earlier video lectures as well. And of course, dp tilde is equal to zdp. Girsanov's theorem plays a role here. So let's be in this setting. And then we have the following findings. First of all, Zt with t between 0 and capital T is a martingale under P. With respect to this filtration script Ft that we have just discussed. Again, this is known. The other thing that is already known to you is that in expectation, Zt is equal to the expected value of z is equal to 1. The third one is also known, that is that the W tilde t 0 less or equal to little t less or equal to capital T is a Brownian motion under P tilde. And the fourth one is new, and that comes from the Martingale representation theorem. That is the following. If we have a process m tilde t, 0 less or equal to little t less or equal to capital T, it's a martingale under P tilde and with respect to the filtration Ft, then there exists an adapted process gamma. Again, gamma between the t between 0 and capital T, such that m tilde t is equal to m tilde 0 plus the integral from 0 to t gamma u dwu. And here's the little technical detail. We have here W tilde. So we would expect filtration F tilde T. But we are dealing with Ft here. Yeah, in order to use the Martingale representation theorem, we will have Ft here. So the technicality is that we are dealing with Ft, but we should be dealing with F tilde T. And in exercise 5.5, this issue is resolved. So there a proof is asked to deal with this. So let me give a remark on this part D to specify it a bit more clearly. Since m tilde T is a martingale with respect to F, then the Martingale representation theorem gives us a representation as an Ito integral. That is the Martingale representation theorem, an Ito integral with respect to W and not with respect to W tilde T. However, the underlying Brownian motion in this case is W tilde T. And we are given that m tilde T is a martingale with respect to F tilde T, 0 less or equal to little t less or equal to capital T. And that is, of course, F tilde T is the smallest sigma algebra, where W tilde S is where S is less or equal to T and is greater or equal to 0. So you see the discrepancy. We have a statement based on filtration F, but we are in fact dealing with a filtration F tilde. And this technicality is resolved in exercise 5.5, and that exercise will be dealt with in one of the exercise sessions. Okay, let's see an application in financial mathematics of this. Again, we know that we had this stock price process. dst is alpha t st dt plus sigma t st dwt under the measure p. And we had our discounting process, dt, discounting capital dt is e to the power minus the integral from 0 to t ru du. Moreover, we know that we have seen that at any time, the value of the portfolio process, xt, is equal to the value of the option, vt, and specifically the discounted portfolio process, capital dt xt, 0 less or equal to little t less or equal to capital T, that is a martingale under p tilde. So by that definition, we have that the discounted process, the discounted option at final time, the expected value under the p tilde measure with the knowledge, with the filtration up to time t, that is the discounted option value at time little t. So now the Martingale representation theorem tells us that there is in fact an adapted process, we call it gamma tilde, with little t between 0 and capital T, such that this discounted option price, dt vt, that is equal to v0, because d0 is equal to 1, v0 plus the integral from 0 to little t of that adapted process gamma tilde u, dw tilde u. So in fact, this is the existence of a gamma, and the existence of a gamma. Now, previously, we have, of course, seen the dynamics for the discounted portfolio process, and the dynamics for the discounted portfolio process were written as follows. The change in the discounted portfolio process is equal to sigma t, delta t, the discount process is at little t, st, dw tilde t. And this gives us, in fact, this is nothing but a different way of writing the following. The discounted option value is equal to v0 plus the integral from 0 to t, sigma s, delta s, discount value at s at s, dw tilde at s. And now we can compare this representation with the previous one, where we see the gamma, and we see that we have, in fact, a construction for the gamma. Right? The gamma, there should exist a gamma, and combining these two expressions give us that the gamma tilde t is in fact equal to this term over here, is equal to sigma t, delta t, the discount process at little t times the stock price process at little t. And this gives us an explicit representation for the delta. The delta from the delta stocks, remember? So delta t out of this equality is equal to gamma tilde t divided by sigma t, the discount factor at time little t times the price process at time little t. And we see that this only goes well when sigma is not equal to 0 and when the stock price process is not equal to 0. But at least we have an expression for that delta function. It's not so easy to do something with this expression. It's more like an existence, right? There is such a process. That is more what the Martingale representation theorem tells us. So in essence, the Martingale representation theorem provides us with a formula for delta t, and it is equal to the amount of stocks in the portfolio. So it guarantees, in fact, that a hedge is always possible. And that delta t, that there is a formula for delta t. The drawback is that the proof of the Martingale representation theorem is an existence proof, and it's not constructive. So it's not so easy to say which particular function this gamma tilde is. So in practice, it's not trivial to find that gamma tilde t process, but we will see later how we handle that. That's it for now. Thank you for your attention.